All right, well, we'll get underway. This is being recorded, and if anybody is interested, we'd be able to make the link available. But thank you, and I'm Doug Britton, and this is a webinar, 3 Steps to Reduce IoT Security Update Frustration While Increasing Deployment Velocity, and the focus is on the yocto-built environment today. So we'll go through some quick introductions. We'll then move to binary internals. A quick review of binary internals and exploitation is kind of a grounding. Then we'll go to the RunSafe Alchemist tools and how they mitigate those and how they drop into Yocto. And our colleagues at Vertiv will then describe a product that makes use of this in their Avocent Core Insight and works alongside Yocto. And we'll walk through some demos of that. So first, introductions. Joerg Weedermann leads the embedded firmware engineering team at Vertiv and oversees the software architecture for Vertiv's Avocent Core Insight firmware stack. Willie Nathan is a product manager for Vertiv's embedded solutions. He has over 20 years of experience engineering and delivering embedded server management solutions. Augustine Goose Roca, is Director of Engineering for Vertiv IT Systems. He leads a global team of professionals delivering the highest quality management solutions in the business. I'm Doug Britton, CTO, and one of the co-founders of RunSafe. Kenton Brazell is a senior field engineer for RunSafe. His responsibilities include working with our customers and pre and post sales and ensuring seamless integration. And Nick Ray is Vice President of Market Development for the commercial go-to-market team at RunSafe. His 20-plus year career spans multiple executive roles in enterprise software and hardware solutions with an emphasis on mobile and cybersecurity. Thank you. All right, so RunSafe's mission is to disrupt hacker economics by immunizing software from cyber attacks. And what we mean by that is exploding attacker costs of exploitation, but at the same time, without defenders having to change anything about their business, how they write code, how they deploy software. We want them to be able to, no changes on the defender's part, but maximal disruption to how an attacker works. And so RunSafe focuses on the most dangerous class of vulnerabilities as a body, and that's the memory-based vulnerabilities. And according to a MITRE study from 2019, it's the #1 weakness of the top 25 software weaknesses. And memory vulnerabilities are things like stack overflows and heap overflows and ROP and JOP attacks. On IoT customers, these impacts are devastating because it causes operations disruptions and staff headaches due to continually patching vendor products. To the device manufacturer, what this also results in is lower profit devices because of the costs that need to be maintained around creating and deploying patches. And it also causes downward pressure on earnings because customers get nervous if there are issues that have popped up. And also, interestingly, 70% of the vulnerabilities patched by Microsoft over the last 12 years have all been memory related. So now what we're going to do is walk through a simple Hello World program. It's a journey from persistent storage, non-volatile RAM, flash, whatever, disk into memory, and then how that gets exploited. So now the loader has taken the Hello World program from disk. It's now copied it into memory, and it looks up the entry point in the program header. Then execution is transitioned to, in this case, function 3, the original entry point, and then execution proceeds as normal. Now, the numbering here is just for convenience, and program flows don't typically move from top to bottom. That's just, illustrative. So let's take a look at that program and say that after Hello World has been deployed, we find out that function 2 has a vulnerability. That could be a stack overflow, heap overflow, use after free. This vulnerability allows the attacker to add instructions at an unauthorized instructions to the stack and run their own program inside of your program. And what they're going to do is they're going to use ROP gadgets, which will be small snippets of code that get stitched together in an order the attacker chooses. So in this case, it's address 0x3b1. There's a small set of instructions that will get used and then return back to the stack, and then we'll jump to 0x1b2. And then because of this overflow, the attacker has been able to write these series of bytes in, and now the program counter is going to jump to each of these gadgets in turn. And what the result is a crude program in program that is going to use your existing program, but rewrite the order of things, and the attacker is going to be able to create their own program. The attacker, the customer has been exposed to this kind of risk from the point that the code has been deployed, even before the vulnerability is known, while waiting for the patch to be applied. So now let's jump into Alchemist. Alchemist is, the exploit we saw was powerful, but it was also fragile. It required perfectly predictable insights into the running memory of the victim process. RunSafe explodes the attacker economics because we deprive the attacker of the information they needed for that exploit to work. So now we'll jump into the RunSafe Alchemist product, which targets these attacks at 3 different points in the customer's software lifecycle: build, deploy, and in your code repositories. Today's discussion is going to focus on build tooling, the Loadtime Function Randomization specifically. The deploy time protection and container repo protections blind the attacker with the same type of randomization concepts, just at other points in the customer's process. So now let's take a look at that same Hello World program with RunSafe's protections added. This discussion isn't going to discuss, we're not going to go into the mechanics of the compilation here. That we would do in a follow-up discussion, or we have other documentation for that. But we're just going to looking at your Hello World binary. How is it now different? So once it got compiled, a dependency was added. We added some extra sections to trampoline into that shared library. We added one extra section, our LFR entry point. Then the entry point of the program is adjusted to point to the new function. And then we added some metadata to the end of the compiled binary. And this metadata has function location and size information. So now if we compare this, what you can see is that the program structure is unchanged. The logic and control flow is the same. The code size changes are extremely small and can be optimized. And there were no compilation changes required by developers. Everything was taken care of by the Yocto layer. And also importantly, no agents were added to the device. So now as that process gets copied from persistent storage into running memory, the process will begin very similarly. We'll jump from the entry point down to the LFR entry point. That will then jump down into the randomized shared library, into the randomized function of the shared library. At that point, the functions in memory will be randomized. Their locations will be completely changed, and this will happen differently for every time the binaries run. And then we do a patch up, because functions may make direct references to other functions, but we are able to go back through all of the functions and patch them up so that they now know for this copy of memory where everything is located. Then execution jumps back to the original entry point, function 3, which is now at a new location, and the program executes as intended. So let's go back and analyze the ROP gadget from the raw native Hello World program and look at how that would have been impacted by LFR. So the first gadget is going to be at, the code snippet was previously at 0x3b1, but it's in function 4, which is now up in the 220 area. And if you were to jump over to 0x3b1, that's, miscellaneous. It's in a random section of another function. And the same is the case if you look at, 01B. So you would have gone, previously that gadget would have been here. But now if you look at that code snippet, it's going to be over here. But there's nothing, that random code snippet isn't actually there anymore. That gadget's now here. So, the exploit will fail. So then the same thing going through the entire ROP chain. So this would happen, and those memory locations would be different for every single time that binary is run. So again, why does Alchemist matter? It leaves the pain. Cost efficiently, you're able to maintain your normal patch cycle. Even if as a new CVE comes up, we recommend applying patches because of course that's prudent, but what it doesn't require is a panicked response of all systems stop, pause, get this done, and your customers haven't been exposed while waiting. So now let's jump into Yocto, and this audience is probably largely familiar with it, but it's an exciting toolkit. It's highly modularized. It's ideal for large-scale deployments. One of its key components is reproducible build, and it's utilized across the IoT spectrum, ARM, x86, and other microcontrollers. RunSafe customers are using, RunSafe Yocto customers are protecting pre-execution environments, akin to what you'll see here from our colleagues at Vertiv, routers, weapon systems, device firmware, and the key value props that keep coming back from our customers is it's a simple layer to add, it's easy to drop in and test. So what we'll do now is jump over to showing how easy that is to add right here. While I make that transition, Nick, had any questions popped up?
No questions yet.
All right, brilliant. Okay, so if you go to our Alchemist portal, and this will be a link that we'll send out in the chat, you'll see, this is where you would go to start a deployment. In this case, because right now this discussion is focusing on Yocto, we'd go to click on Yocto projects, and then you'll get to start walking through a series of steps. And I'm on if you can't see my background, I'm on a beach, and it appears that my cell Wi-Fi hotspot might be a little flaky there. Okay, so the first thing you would do is select the Yocto distribution that you're working with, and these steps are designed assuming you're starting from a blank slate with Yocto. You wouldn't need to clone the repo if you're on a box that's already has the Yocto toolkit on it, but you would need to, under step 2 of 7, clone the LFR meta layer. That would come down. So inside the LFR layer, you'd need to add the license key, which you would have gotten from this self-service portal when you registered, and then you'd add the layer in through BitBake, and then you would tell it what kind of machine you're building, and then you'd run BitBake, and you'd also be able to see in here how that you are able to verify, because everything happened normally. Someone can wonder how would you know if this was even added in the first place? We give you some commands down at the bottom to be able to show for yourself that in fact there has been a change in your binaries. So then we can go back to, and everyone will be able to register and apply this themselves. So now maybe we can jump over to my colleague Joerg, and he can start showing how this is being applied inside the Vertiv environment. Joerg, you might be muted.
While we're transitioning, we did actually get a question, Doug, and so maybe we can answer that live. The question was, how does this compare to ASLR or pre-link randomization?
So one of the big differences, so ASLR is not very granular. And what you're doing is randomizing offsets, you know, the base offset for an entire process. This is far more granular. We kind of describe it as, you know, one is randomizing the boulders on a beach versus randomizing the grains of sand inside the boulders on the beach. So a completely different quantum of randomization.
Great, thank you.
Okay.
Yep.
Well,
thank you, Joerg.
Yeah, thanks, Doug. And yeah, please continue post your questions. Before we talk about you know, what's our journey with RunSafe been so far, just want to give a quick overview of what type of product we are talking about. So the Vertiv IT systems group that I'm working for provides solutions and products to remotely manage your data center, right? Your data center infrastructure and your equipment, right? Some of you might be familiar with our products as our group was formerly known as Avocent, hence the name of Avocent Core Insight for this product. So specifically, specifically what we are talking about now though, is the Avocent Core Insight firmware. And that's essentially a firmware package, actually a suite of firmware and tools for service processors, also called BMCs or baseboard management controllers. And I don't know, many of you might be familiar with that concept, but essentially what that is the baseboard management controller is a little chip, an SoC that's usually integrated on the motherboards of servers, but not only servers, but more and more storage and networking like switch and router devices do the same. And those SoCs have their own network connection, right? They have their own power. So it's a very independent unit, always accessible from external, even out of band, even if the server OS is not booted and so on. And it provides you pretty powerful functions like, you know, powering on, off, reset the server, right? Giving you remote keyboard, video, and mouse access to really control that server as if you were there, and getting information about its health, right? Getting information about the environmental conditions that the server is operating in. And sometimes you can even recover a server that's not in a good state, right? All the way up to some organizations using, you know, a BMC to even provision that server all the way from the ground up, from bare metal, right? So it's a really critical component in your IT infrastructure. So that's really what basically Avocent Core Insight is, a BMC firmware. Now, what's that related to Yocto? Now, our entire build system has been transformed into a yocto-built. That's not always been the case. So historically, we have been dealing with, you know, the more traditional makefile approach. That's been working for quite a while, but you quickly realize that, you know, you get into limits on, you know, how you can customize, how you can maintain your build system, how you can add features or you know, leverage or moving things around and make it more modular, right? So Yocto does a lot of good things for you. And let me just summarize that really quick, even though I realize maybe many of you are familiar with Yocto, but some might still be deciding. So Yocto has a really large community, right? It's becoming kind of an industry standard for embedded software. So you get a lot of documentation, it's widely used, right? And you get pretty frequent releases, which helps you stay up to date with bug fixes. What's also important is that actually kind of out of the box, Yocto already comes with a lot of ready to use hardware platforms. If the one of your choice is not there, chances are that your hardware vendor might even already provide a Yocto board support package for the particular processor that you're using, or you can easily just, you know, basically build your own as an additional layer and add it to the build system. Then there is this feature of binary reproducibility, and I think that's pretty important, especially when it comes to like working in large globally distributed teams like we do. Like every team has its own kind of build servers that they want to use. Even individual developers might want to use their own Linux machines to build, right? And so this build system is designed to build everything from scratch, right? Everything from source, including the actual cross-compiler tool chain. So you're pretty much guaranteed that you're getting the same binary output regardless of where and how you're building. Additionally, there is concepts built into Yocto that really ensure that you're using the exact right source that you actually want to build, right? Especially when you're using a lot of open source where there's like many different versions and they're constantly evolving. There's checks and mechanisms that help you really ensure your build is consistent. And last, but not the least at all, the concept of layers. So layers is probably the most powerful concept in Yocto, which allows you to basically group your source code modules together. And then once you have them grouped into those kind of so-called layers, you can easily move things around. You can actually place them anywhere in your build tree, which has historically been a challenge when you use like traditional makefile-based systems where there's a lot of path names to be worried about. But here, once you have grouped certain functional modules into a layer, you can move them not only within the build tree, but you can even leverage them into other build trees, right? If you have different products that reuse some of your components, just migrate that layer to other build trees. You can also just by turning on and off or removing those layers, you can turn on and off features easily for different products that you might be building based on the same source. And last but not least, the very positive side effect of using these layers is that in a multi-vendor scenario, like in this case, we're working with RunSafe, for example, but you might also work with other vendors. You can quite easily exchange pieces or parts of your firmware, right? By just adding layers of code from either other teams in your organization or from third parties. Okay. So let's, before we dive deeper into the RunSafe transformations in our firmware, let's take a quick look on how that firmware stack actually looks like. So here's a kind of a conceptual picture. It's by all means not meant to be complete in terms of its content in that firmware, but it visualizes that there's a lot of individual functional modules and components involved. And they're grouped here by color. So there's all these gray modules, which include the Linux kernel, a dbus for creating a data communication grid that easily makes multiple modules fit together. And all of those gray modules are actually what's called the openBMC. So some of you in the audience might be familiar or have heard about it, or maybe even using it. It's for us, it's basically the base layer, if you want so, or like you could view it as one large open source component that comes already with a lot of functionality in it. And then we are building our IP on top of this. Or in some cases, we might slightly modify some of the components or replace components by our own versions of it. So for instance, that we are adding, let's say, a security manager and a couple of other modules that we then call this group of modules, we would call them, for instance, foundation. Right? So, and then we're packaging those into a Yocto layer. Right? And similar for other functionality that we are adding. For example, all these blue modules at the upper right, they're building a powerful and very flexible Redfish stack, including a web UI that also uses Redfish. Now, this itself, this subsystem of functionality itself is built from many modules, but we are grouping them into a Yocto layer, which we call essentials. And then last but not least, there is all the keyboard, video, mouse redirection, and virtual media functionality. That's more in pink on the right-hand side, which we call it the advanced layer. And so by grouping that into layers, not only are you able to quickly remove and add those layers into your build, but you can also build a product structure around that. Like we do in our case, where we can offer an essential or an advanced product, depending on the customer's need. Now, how do we apply the RunSafe technology to this now? Well, first of all, why are we? I should mention really why are we actually applying RunSafe technology? Now, you heard a lot already from Doug about what that technology actually does, but as I mentioned earlier, BMC is a very critical infrastructure ingredient in your data center, and due to all its external interfaces and network interfaces and APIs that are all externally accessible, it's traditionally been a nice target for cyber attacks, right? So no wonder that we really need to apply an additional layer of security to such a firmware, which we do, and we do that in a few very simple steps. So no wonder it actually becomes a layer, right? In our build system, we just create basically a new meta layer. You can also, like Doug showed, you can also just download the meta layer from RunSafe. You might want to massage it according to your needs, but essentially there is these ingredients in that layer. There is the actual LFR package, which is essentially that secret ingredient, the binary code that basically does the actual transformation. And then there is a so-called BB class, which is really it's a Yocto concept where into that class you can package a whole set of flags and settings and configurations. In this case, it would be additional GCC or linker flags, right? That you're packaging into that class. And then with just one additional line, one additional instruction in Yocto, which is the inherit instruction that you're packaging into that layer, you automatically apply this transformation to all of your recipes, pretty much all of your components in the scope of your yocto-built tree. That's just visualized with those arrows, but really it would actually affect all of the modules at once, at least all the ones that use the GCC and the LD. Now, there might be situations where you want to exclude certain of those modules for the one or the other reason. So that's also fairly easily be done using the yocto-built system. You don't have to go into those individual individual modules, like in this case, the KCS module. You don't have to go in there and do any modifications. Instead, you're putting individual exclusion statements in one central place, which is that actual randomize BB class in the RunSafe layer. And it will have its according effect to that module that you want to exclude. And so last but not least, if as a developer, you just want to quickly turn off all the transformations, being it for like the purpose of troubleshooting or debugging.
We might have lost Joerg's audio. While we see where we are on that, I will jump in with a question, and then if we don't get Joerg back, Kenton will jump in with a demo. So Ken, if you could get that teed up while we jump in with this question. So one of the questions asked was, what is the performance impact of applying Alkemist? So what we provide the performance on size, so it depends, and this is tweakable. based on your needs, but it could be as much as 10 to 15% in terms of extra size, and sometimes it's less. Sometimes it's it has to do with the essentially density of functions. But then the last thing is size or performance impact. So there's no runtime performance impact. So meaning once your code is up and running, it performs exactly the same speed as it otherwise would have. And that's, again, going back to the description of how it works. We're not changing, the instruction count. We're not changing those things. They're on startup. What we're noticing in a full yocto-built environment is something in the range of, 10 to 15% startup cost. So meaning if something took 10 seconds to load, it might now take 11 seconds to load. But then once it's up and running, it's it will continue as normal. And again, those things are tweakable. We can help you if size is your constraint. We can help you manage size down, or speed is your constraint. We can help you manage that. So thank you. And Ken, let's walk through the demos. And this will be a demo focusing on the exploitation.
Yeah. All right. Thanks, Doug. So I'm going to close out our time by showing you a demo of the tech that we've discussed today. While we've gone over how RunSafe Alchemist integrates and protects in Yocto environments, much like with our partners at Vertiv, we thought it would be worthwhile to actually show you the technology in action. To do this, we've created a live exploit of a Hello World style program that contains a buffer overflow vulnerability. We'll go through each step of the kill chain, bringing to life Doug's earlier explanation of how memory-based attacks work. Upon exploitation of the vulnerable program, the attacker, in this case myself, will gain root control of the Docker container that the program is running in. After establishing the baseline for the original file and exploit, we will harden that same file and repeat that exploit. Improve the Alchemist hardening renders the same exploit inert. While this exploit is a Hello World file and in a Docker-based environment, the technology and protections applied function the same for any third-party or proprietary software that would be found in your Yocto builds. For our demo, we'll actually be shifting our focus back to the Alchemist portal at alchemist.runsafesecurity.com. And this is the same location Doug showed you earlier when reviewing the instructions for deployment of Alchemist in Yocto. On the screen, you can see the demo tab with some notes at the top on the environment and the list of the 3 currently available demos that we have today. Again, these are focused around Alchemist source protections, reviewing the complete story of building, proving the technology, and finally integrating into Docker environments on a variety of open source and Hello World programs. With all that being said, let's jump right into it. As we start the demo, let me set the stage for you a little bit on what you're seeing on the screen. On the left, you can see a guide with instructions and helpful shortcuts. On the upper right is a live text editor for files, and on the lower right is a live terminal for entering commands. I wanted to point this out not only to give you a reference for the page, but also to drive home that the actual editing, building, and running of the files will be happening live on servers and working in real time. All of these panels are interactive and operate just as they would if you were logged onto the server directly. So now let's talk about what's actually happening. In the lower right, you can see that a Docker image is building automatically in the terminal window. This is actually building the unprotected, original, and vulnerable version of our Hello World binary. If I click the Dockerfile link in the text editor, you can actually see what is being built. This Docker file is what we will modify in later steps by adding Alchemist source protections to it, and then building it and comparing the outcomes of the ROP attack against both images. Now, I promised you another review of a memory corruption kill chain and all the components needed to make an exploit work. So let's start with the vulnerable program itself. Verify password, as you can see up here, is a simple compiled program written in C that is carrying out a typical password authentication check. If the password entered is correct, then the program returns a secret phrase. The unchecked buffer input allows a bad actor to overwrite the return of the function, which was originally supposed to return to main, but instead is redirected towards the attacker payload. Much like any real-world piece of software, there is a shared library that the verify password program needs to operate correctly. It is in this library that the second piece of our kill chain is found, the exploitable payload of a system call to bash in the call bash helper function. This function, which gives a user admin control, is harmless in normal operation. In our real-world representative use case, this function was used only for debug purposes and should have been deleted before the release. As it was not caught, we now have a 0-day vulnerability and lethal payload. At this point, all we need is a third piece of the kill chain, the exploit script, to actually string the ROP gadgets together to link the vulnerability to the payload. The exploit verify password Python script is the example of the output an attacker would create after researching the binary and library, finding the vulnerability, and establishing the payload, and maneuvering the memory map to link the two. Let's quickly look a little deeper at the exploit file to understand how that happens. First, we need to find the base address of the library in memory and the address of the ROP gadget. Next, we need to fill up and overflow the unchecked buffer to redirect the return address to the call bash helper function in the library, which contains the payload, in this case, root access. Finally, this input into the verify password function with the ROP exploit as its argument is the last piece of the puzzle we need to achieve a successful attack. As you can see, a known stationary recurring memory address is the crucial component to taking this devastating attack out of attackers' labs and into the field on real-world systems. Considering IoT and embedded devices and the scale at which a successful attack like this could hit an enterprise, it's easy to see how RunSafe technology and introducing binary diversity at the lowest levels of code are critical to securing Yocto environments. Inserting that randomization through Alchemist integration forces attackers' targets to go mobile, and as you will see, eliminates the repeatability of crafted attacks like these. Now that we've touched on the entire kill chain, let's move on to step 2. This step is verifying that the original version of the Docker image was built properly. I can click on the link to the left here, but for show, I'll just type the command in the window. As you can see, it was indeed created just a short time ago, and let's move on to step 3. In this step, we will test the program functionality and use our established kill chain to take control of the unprotected image we just built. The first command is just running the image to show the functionality and inputting the correct password, which is super secure. Clicking on the shortcut, you can see the command execute in the terminal window. As the input was correct, the secret phrase, which is the RunSafe slogan, 0 days are numbered, is displayed. Scrolling down to our next command shortcut is where we finally run our Python attack script in the same environment and against the same unprotected image. The output now displays log data from the exploit script, which reveals that the base address and ROP gadget offset to that address was found. That information was then used in the string which overflowed the buffer. At first glance, you might think that the program worked normally because of the notice of incorrect password being displayed. However, due to the buffer overflow that redirected the return of the function to the payload in the library, a shell prompt is now running within the container. By typing in commands such as ls or who am I, you can see that an attacker now has complete control. Let's exit the state and immunize this program using Alkemist. As we are doing all of this live, we have to actually rebuild the Docker image, this time with Alkemist source protections integrated at compile time. Those that are familiar with Docker will recognize these simple commands, but I'll review their general functionality and why we need to add them to enable the hardening of this image. First, we need to check that the Docker file is open for editing before we make modifications. And then the first change we'll need to make is to add a new stage. We need to add the RunSafe security Alchemist Debian image that contains the Alchemist code and executes the license verification. Next, we need to copy files from the added LFR stage. We do this by establishing an environment variable and using the copy command to move the files to the proper directory. Lastly, we need to insert the LFR helper script and cleanup script. The helper script does the heavy lifting of actually integrating Alchemist technology with the software during compile time, and the cleanup script removes any excessive files that won't be needed during the hardened binaries runtime. I can now kick off the build of the new protected image, which is the same command as before, just with the addition of the Alchemist license key argument. In an effort to provide a direct comparison of these steps to Yocto, let's tab over to the integration guide that we were referenced earlier. And the first steps are focused on pulling in the Alchemist LFR files and integrating that layer in the build environment. The last steps use bitbake commands to build the image and apply complete Alchemist protection during that time, as well as providing a method for verifying hardening is in place. While these technical steps are obviously different, the procedure is effectively the same. Tabbing back to the demo itself, we can continue to the final step. This last step focuses on two things: proving identical functionality and proving Alchemist protections work against the exploit. Just to refresh, let's rerun the first two commands on the original binary to show the original program functionality and the effect of the ROP attack. So again, showing the password input super secure and the output 0 days are numbered. Then the exploit, which opens up root control on the container. The next two commands are the exact same, just executed against our Alchemist protected image. A small note, these commands will open a new terminal so you can see the protected versus unprotected side by side. First, we verify the functionality remains the same. As you can see, password authentication program still operates normally. And then running the second command and attempting the Python exploit, you can see that LFR successfully randomized the memory layout, immunizing the software and preventing the attack. Due to the attack failing to hit its target, a shell is not open, root access is not attained, and the container stays secure. In looking at this side-by-side view, it's easy to see how a simple solution such as adding in randomization is crippling to the biggest threats to cybersecurity today. At this point, we've reached the end of the demo, and hopefully you were able to follow along and could see how this technology is relevant to the systems and software you care about. Before I hand it back to Doug for some closing statements and Q&A, I wanted to encourage you all to go to our Alchemist portal, which is again at alchemist.runsafesecurity.com, and register for a no obligation account. This will allow you not only to revisit the demo on your own and in your own time, but it will also allow you the ability to try integrating Alchemist source protections into your dev environments of Yocto and many others. This portal is a key outreach tool that we have built and are expanding on, that we provide to the community to share with what we're doing and how we're making it easier for the world to stay safe, at least in cyber defense. On that note, I thank you for listening and hand it back to Doug.
Thank you very much. Demo. We have one question regarding what process architecture is supported. Sorry, we got one question regarding what process architecture is supported. ARM, ARM, M, the M8 core processors, so that's not a problem. And if there are other processor architectures, we've been able to do those environments, so please reach out if there's a concern. And the RunSafe, another question about
Yeah, it's pretty tough to hear you. Yeah. Where were we at, Nick? Did you have a what was the question, I guess?
The question that Doug was attempting to answer was specific to processor architectures that are supported.
Yeah, the so for Yocto specifically, we're looking at x86, and you know, we're working on PowerPC. We're rapidly expanding inside that space.
Or the ARM Cortex A and M.
Yeah.
On the big util question.
And there was one other question, Kenton, I think this one was for you. What tools are you using to run the demo?
This is a so it's a service we actually use that runs a, you know, it's sort of a software as a service offering that kind of gives you a sandbox environment to play in, that you know, you can import different things, and we've got a couple different demos that are based around Docker and LFR. So we bring in to that specific stood up server what needs to be added, and sort of minimalist run the demo, whether it's building or running the exploit, or actually you know, performing some of the verification steps and whatnot.
Awesome, thanks, Kenton. This is Shane Fry, joining in a little late here, but answering questions on behalf of Doug. There's a question around what version of GCC or bin utils are we compatible with. For the most part, it's really any and all versions. There's a super old version, like I think 221 or something, where we had some, there were some linker bugs that got fixed that don't work with, or before those bugs were fixed, we had some problems with that. And then if you're on 231 of bin utils for Debian-based systems, there's a problem there that they broke functionality and have fixed that. But I think for Yocto, we ship a linker for that, so you don't have to worry about that problem itself. As far as versions of GCC, you know, all the way up to the latest, I think we're getting ready to release support for the latest Yocto release 3.1 Dunfell, which I believe is GCC 9 or 10. And so that should work there as well. That is kind of one of the nice things about our solution is we don't force you to use a specific version of the compiler or our version. We're not selling you a security compiler. So we don't want to be in that business. So you can use whatever version you currently have.
Yeah, Shane, and I can confirm we are using, or in the middle of preparing, the GCC 10 support. So you do support GCC 10 as well. And we have that support in Yocto 3.1 as well. So.
Awesome. Thank you, Joerg.
If there's any other questions, feel free to enter them into the Q&A. So far, I think we've answered them all from what I can tell. I think we're good. So at that point, Doug, given the audio challenges as Nick at RunSafe, I'll go ahead and close it out, but want to thank everybody for their attendance and participation. And big thanks to our friends over at Vertiv. Joerg, great presentation. Appreciate you running through your integration of Alkemist into the Avocent Core Insight products. It's been fantastic working with you, and it's a great example of the collaboration between RunSafe and Alkemist against the Yocto project overall. So great session. Appreciate all the information and all the great questions. And with that, I think we will wrap. Take care, everybody.
Thanks, everyone.
Thanks, everyone. Bye-bye.
Thank you.